Okay, these sections on chapter 4 sections, I believe 4 through 6 are all about circular motion. And the slides, to be honest, are a little bit out of order with how I would present it. Not trying to make these uh, sessions immediate follow-ups of the slides, but at the same time, there's some terminology that we need to make sure we're aware of. And I'll expound a little bit on these slides. Right, so the first thing we talk about is uniform circular motion. That's an object, right? Oops, that's an object moving in a circle at constant speed. And if it's moving in a constant, we define the period of, yeah, so a few things. We obviously the circumference, the circumference, but we define speed. This is the first thing in circular motion. We define the speed of a particle in circular motion as that's the simple distance over time formula. But a complete rotation is called a period of rotation. And that's letter capital T. And obviously the circumference. And you notice how the velocity vectors are always perpendicular to the position vector. Because if we're doing physics in a real coordinate system, I'm going to skip this example. If we do, I'm going to go to full screen actually as well. If we do physics in a coordinate system like we're supposed to, what we're going to find is that this is a vector, right? This is a vector right here, and the vector is, what would be the expression for this vector? Well, in the XY coordinate system, it's going to be in terms of this R and this theta, well, this position vector will be vector R equals, it'll be equals R cosine theta in the I hat direction plus R sine theta in the j hat direction. And that's pretty simple. I mean, we know what those values are from just looking at the right triangle. What would be the velocity though? The velocity would be the derivative, obviously, of the displacement. So dr over dt. What's the derivative of this with respect to t? Well, we assume for all these conversations about circular motion that the radius is constant, and so, but we're not taking dr d theta. We're not taking dr d theta. We're taking dr dt, and so we need to add the chain rule here. Yeah, so this would be d theta over d theta. We need to multiply by 1. And so what is that velocity then? I'll just write it here. Velocity vector. Well, what's the derivative of cosine? It's minus sine, but we need to do the chain rule. So we get minus r sine of theta times d theta dt in the I hat direction. And then the same thing for the j hat direction. If I have enough space, it'll be r cosine theta d theta dt in the j hat direction. Now, looking at that expression, it's not clear where that points. But certainly we can factor out the r and the omega d theta dt. If we factor those out, then we got minus sine theta I hat plus cosine theta j hat. Where does that point? Well, we know cosine theta I hat plus cosine theta I hat plus sine theta j hat points up and to the right. Well, it turns out that minus sine I hat and cosine j hat points up and to the left, actually. And so that's kind of how you verify that this velocity vector is indeed, drawing it up here, this is indeed pointing up like that. And the magnitude of that is the speed, which would be circumference over period if it's moving in a circle. But you get the impression that these r's and these v's and even these acceleration vectors, they're pretty confusing because at every second they're constantly changing. And they're not changing in a way that lends itself easy to work with equations directly with them. And so that's why we need to introduce this concept of angular position. So angular position is the kinematic variable you would expect that starts from the positive x-axis and increases counterclockwise. Well, what do you do once you've got angular position? Well, then you define angular displacement. And then from angular displacement, you define angular velocity. That's the next slide right here. So looking at this figure, it's pretty straightforward because we got an initial position like a theta sub I. Oh yeah, that's right there. Okay, yeah, you have to, okay, I see what they did. Yeah, you have to be careful here. So this little angle is theta sub I, this big angle is theta sub F, and so delta theta is, you can follow this pretty clearly. It's the vector derivative. Oh, okay, sorry. There you go. That's the displacement, and so that, much like in the position sense, that's how we define average angular velocity right here. And then, as is usual, that's a measurement that you make. And then in the limit, as the time interval between these measurements gets closer and closer to zero, then we got our instantaneous angular velocity, which we'll almost always be exclusively referring to as just omega. So omega is then the derivative of theta with respect to t. So I have to do some basic setup. And the signs, actually, a couple of things to mention about this. There's a lot to read, and you can certainly read through it on your own. One thing I would mention is that the signs of, what does the signs of omega mean? Well, let me erase all that stuff, actually. The signs of omega, if omega is positive, that means we're rotating counterclockwise. If omega is negative, then we are rotating clockwise. It's always opposite. And then we also have this uniform motion relationship for a particle moving in uniform circular motion, right? If it's not speeding up or slowing down its rate of rotation, yeah, I'll generally call omega rate of rotation. I think that makes the most sense when we're talking about a circle. But we got this uniform motion model, uniform circular motion model that we can use when we've got particles that are just rotating at a constant rate in a circle. Okay, so we got this quick check question, and I want to spend a little bit of time working on this quick check question. So let me launch the poll. In looking at this example, where do we find displacement? Because the question is asking how many revolutions. Well, we've got a graph of revolutions per second. So they're asking for delta theta, right? They're not asking for actual position. And we just established that delta theta is or omega is the derivative of displacement. And so clearly this will be the integral. So this is a time varying angular velocity. And so the displacement, which we fortunately don't need to do any conversions like radians to revs or degrees to revs or whatever. We just need to find the area of this trapezoid. Okay. The quickest way, in my opinion, to find this area is to look at these squares. Notice that each of these squares have magnitude 1, and the half squares have magnitude half, and so this entire area has a area of 6. Okay, and then from that, that's all we need. But I want to expand a little bit on this problem. Certainly show you the answer. It's 6 revolutions. But I want to expand on this problem a little bit and talk about the graphs of not only angular position versus time, but also use it to introduce angular acceleration versus time. So I'm going to switch the whiteboard. Just a quick second. Okay, so what we want to do is want to graph we'll graph the angular velocity vector, or yeah, the angular velocity graph first. It in fact is a vector. I may mention that a little bit, but it looks like the trapezoid, like we saw in the graph, 2 seconds and 4 seconds. Now if the thing is speeding up or slowing down its rate of rotation, then its angular velocity vector itself is changing. And so we define what's called the angular acceleration vector, and that angular acceleration vector is the slope of the angular velocity graph. And so what's the slope here? Well, this was 2, and so the slope is 1, but it has units, and so this is 1 revolution per second squared, actually, and then it jumps down to 0. Okay, that's the graph of angular acceleration versus time. Now, typically we would draw the angular position vector directly above it, but I want to give it more space, and so I'm going to draw it to the right of the angular of these two. I want to consider what this graph looks like. Now, we don't automatically know that our angular position is 0. That's one thing we weren't given in the problem. So we can assume actually that we just start at some initial value. What does this look like? What does the graph of angular position look like? Well, the best way to do that is to look at the slope that the graph inherits from its derivative, right? Omega is obviously d omega dt. And so omega gives us a graph of the slopes of theta. So at time t equals 0, the slope is 0. At 1 second, the slope is 1. At 2 seconds, the slope is 2. The slopes are getting bigger. And then it maintains that slope until 4 seconds. Okay, so that's where the information about omega shows up in the information or in the position graph. And so this is a parabola. It's not perfect. But these graphs never are when you're drawing them. And then it just kind of maintains that slope all the way to the end. So if I were to draw it better, it'd be something like a parabola and then shooting off like that. And then, so on the left side, it's a parabola. On the right side, it's a line. And you'll remember this from the 100-meter dash example that we did last week, where we modeled the sprinter as having constant acceleration followed by max speed for the remainder of the race. So this is a good starting point for anything that you get rotating from rest. When you get it rotating, you have to give it some angular acceleration. Once you give it an angular acceleration for a brief time, it's going to have a rotation that will actually stay steady unless frictional bearings or air resistance or anything like that gets it to slow down. Okay. Quick question to consider: what is the change in position after 2 seconds? Not just the whole thing. If we go back to the graph, here, what is the change in position between 0 and 2 seconds? How do we reason about that if it's not the entire thing? The change in position in the first 2 seconds is just the area under this curve for the first 2 seconds. I don't actually have the right slide. I'm sorry. Let me navigate to the right one. If it'll let me. Yeah. Going back to this slide, right. Yeah, going back to this slide, the area of, full screen. The area of the first 2 seconds, how you reason about it, is it's also just the area. The displacement in a velocity graph is the area. So for the first half second, that little scribble that I just made, for the first second, the displacement is only 1/2 of a revolution. So for the first second, it's only made 1/2 turn. Between 1 and 2 seconds, it makes 1.5 turns. So that means for the first 2 seconds, this displacement is 2 revolutions. So always remember that the displacement is the area under the velocity curve, and change in velocity is the area under the acceleration curve. So yeah, that's a helpful example to go through. Yeah, and the slope of the position graph is inherited from the velocity graph. Okay, continuing our brief review of these slides. Oh, this is a quick example. Here's another quick check question. On a ball rolling down. Let me set up the poll. If we look at this example, the period of rotation is defined as the time it takes to sweep out an entire angle. Oops, I'll turn this around. Rate of rotation, or angular velocity, can be defined as the time it takes to sweep out an entire circle over the period. And this is only for from uniform circular motion. Not necessarily, this is a general definition. And so the period then is flipped around, right? So the period is just 2 pi radians over the angular velocity, which in this case is 4 pi radians per second. And you can, when you recognize that, then you can see that, oh yeah, it's just 2 pi over 4 pi, which is just a half. So that is the answer. Yeah. That one wasn't too hard. Okay. With the last few minutes that we have today, I'm going to go on the whiteboard and sort of justify the centripetal acceleration formula. They do it on a textbook. From my experience, I think it's helpful to see it done in real time and try and emphasize the main parts of that explanation. So here's the key idea to this centripetal acceleration, right? So a particle, let's just do this derivation. So if a particle is rotating, say, counterclockwise, right, it's got an initial position vector and a final position vector, right, in a time interval. And it'll have its initial velocity and its final velocity in a time interval. Well, there's 2 different circles here. There's the circle of the position, and then there's the circle of the velocity. And so as these 2 move, they both sweep out the same angles. It's the same like delta theta here. And so what's the displacement? What's the displacement of the particle? Well, it's obviously position final minus initial position, which it's like the vector connecting this little triangle on the circle. Okay, it's obviously final is position minus initial position, but in using the formula for the sector of a circle, or the arc length of a sector, oops, here we go. Yeah, theta r, that's not really a good radius. an arc length. Those are all related by arc length is r times theta, which if you're not comfortable with this formula, just think about the circumference of a circle. The circumference of a circle is a special case of that formula. So the formula for the displacement in circular motion then is just the radius times the change in angle. Well, what's the velocity? The velocity is defined as delta r over delta t. So if you just plug that straight in, you have constant r, and you have delta theta over delta t. And so we derived our first simple expression for velocity as being r omega. That's one we actually get for free. But what about acceleration? What's about the expression for the acceleration? Well, that is delta v. Let's talk about, instead of the acceleration, let's do the magnitude. That's delta v over delta t. Well, delta v, the thing I want us to see is that delta v is also rotating. So as the particle rotates in its standard xy coordinate system, the velocity vector is also rotating in its own coordinate system. We have Vx and you have Vy, but if the position vectors are rotating in the first quadrant, the velocity vectors are rotating in the second quadrant. They're rotating at the same rate, and which means they sweep out the same angle, delta theta, and so the change in velocity vector, delta v, it's like its own little arc length formula. So that delta v equals the size v times delta theta. And you can even do this for acceleration too. The change in the acceleration at every instant is also the magnitude times delta theta, which is really interesting. That just continues. Delta t, that's supposed to be a delta t. So in the numerator for this acceleration, we put v delta theta. And for delta t, we just use, the definition of velocity. So this is delta t is let's see, well, sometimes you just gotta write it out. Flip this, cross multiply these two. So delta t is delta r over v. Delta r over v. But now how are delta theta and delta r related? Well, either way, it's either v d theta, and delta r, as we just established up there, is r delta theta. And so when the smoke clears on this calculation, the stuff cancels. The delta theta cancels. The v's multiply, and so you get v squared over r. Which is a really curious result. So this is the formula for the magnitude of the acceleration that the particle has as it moves in a circle. The very fact that it's moving in a circle, not necessarily speeding up or slowing down. So even if a particle has constant speed, then if it's going in a circle, its acceleration is constant. And so I intentionally did not give us the direction because I want to bring that to a quick check question that we'll do in a second. Let's see. So I'm going to switch to full screen mode. There we go. Okay. Let me give you the next quick check question. Okay, so in switching to the quick check questions, we have here we go. Now the first one is kind of a gimme because I just said it. So I'm not even going to run the poll on this one. So traveling around a curve at a steady 40 miles an hour, Is the car actually accelerating? I just said yes. So it's yes. But now let's dig deeper and ask, well, if it is, then what is the direction? Let's launch this thing. Question. So let's take a look at these vectors, because one of them, I mean, they all make sense actually, but I think in this example, it's most helpful to just use the definition of the fact that acceleration is in the same direction as change in velocity. So at this instant, right, we're moving forward and our speed is a steady 45, right? So we got V initial. Well, some instant in time later, maybe the car is over here. It's the velocity has the same magnitude, but now it's changed the direction. So this would be final. What's delta V? What's the direction of the change in velocity? Because if we're changing velocities in one direction, our acceleration has to be in the same direction. Excuse me, these vectors are defined to be the exact same direction. And so if we do that, let's take our final, right? Let's take our final velocity minus our initial velocity. What's our final? Our final points mainly to the left, slightly up, right? And then what's our minus initial? Our minus initial points, well, if our V initial points up and to the left, then our minus V initial will point down and to the right. And so we're going to add that to our V final, and we'll get something like, we'll get something like this. Minus V initial. And so we see that our change in velocity vector points down and to the left, which then we can infer that also acceleration points down and to the left. Of course, this isn't a perfect drawing, but acceleration is a little bit more angled. But that was the only choice. And so that's one argument for why the acceleration points down and to the left. Looks like not many people mentioned it in the polls, but what about our feeling? I mean, we're learning this stuff, but we're not learning it in a vacuum, in the sense that we have plenty of experience about motion coming into a physics class, and that's not to mention even folks that have taken physics before. Why is it not accelerating in the direction of, which choice is that? D. D is, it points outward. So you imagine you're in this car, you're making this left turn. Well, you feel pushed out in that direction of D. So why aren't we accelerating that way? And that's a really good question, because even though we're not, these vectors tell us that we're accelerating down and to the left, but our feelings, we feel pulled up and to the right in this top view. And that the reason is because we're always accelerating opposite what we feel when we're accelerating. Now, the only difference is when we're like on a merry-go-round or something. That's a different story, because the thing's rotating. The system that we're on is like rotating in a weird way. But in these typical examples of like on the elevator or driving in a car, whenever we feel a pull in some direction, we're actually accelerating in the direction exactly opposite of that pull. And so let's do another example. Yeah, the correct answer is the down and to the left one. Let's do one more where we have a car that's going up a circular hill while slowing down. So how to explain this one? Two different ways. I mean, the first way is the most direct way, and that is, again, by directly finding a change in velocity vector, because we know that the change in velocity vector has to be proportional in the same direction as acceleration. So like v final minus v initial, these two vectors are fine. You have to be careful, make sure you can find where the starting point of these things are, and make those a little bit bigger. I know that I certainly could use as much help as I can get. Okay, so those are the two vectors. So let's do our little vector subtraction. Let's take so the one on the right, that's v final. And the one on the left is v initial. Right, v initial is a little bit bigger. So we're going to take that, invert it, and put it at the tip of v final. Right, so this is minus v initial. And now we just connect the arrows. So delta v ends up being the third leg in this triangle. Right, and so just by a simple vector subtraction, we see that delta v points down and to the right, which means that acceleration also has to point down into, down and to the left, excuse me. That's one justification for this question. Another one is perhaps a little bit more interesting in terms of what the book suggests. The thing is that we're moving in a circle and we're slowing down. So if we're moving in a circle and slowing down, then at this point, well, we have to have, if we're moving in a circle, that means we have to have an acceleration, call that a perpendicular. We have to have an acceleration towards the center of the circle, since we're moving in a circle. But since we're slowing down, we also have to have an acceleration that points against the motion. So this is like the velocity intermediate. Okay, so it's possible when we're moving in a circle and either increasing or decreasing speed, we have to have an acceleration that points towards the center, but we can also have an acceleration that points tangent. And in this case, it points backwards. And so this vector sum gives us more or less the same direction of our acceleration. So those are two different explanations of why the acceleration indeed points down and to the left. Okay. How are these two related? Well, they're kind of not. They're sort of independent vectors, because I would say in some sense the centripetal acceleration is kind of dependent on the tangential one, because the tangential one is usually, well, the tangential one usually affects how fast it's going. And then once you know how fast it's going, then the centripetal one is then, how fast it's going over the radius. And then, of course, the tangential acceleration is proportional to the rate it's proportional to the angular acceleration, the one that is the derivative of the alpha, or the omega. So these are some slides summarizing that. Is this question any good? Yeah, actually, this isn't bad. Yeah, okay. So we have two people. Yeah, let's do this poll. Just kind of, do we know this, how these things are related?